Welcome to Module 1, Foundations of Artificial Intelligence and Machine Learning. This opening module establishes the conceptual ground for the rest of the course. Before evaluating models, interpret predictions, comparing algorithms, or discuss applications, we need to understand what artificial intelligence and machine learning mean as fields of study and as practical technology. Artificial intelligence, abbreviated as AI, refers to the broad effort to design computational systems that can perform tasks normally associated with human intelligence. Those tasks may involve reasoning through a problem, recognizing patterns, interpreting information from the environment, making decisions, learning from experience, or adapting behavior over time. In this sense, AI is not one single technique. It is a broad area that brings together computer science, statistics, mathematics, cognitive science, engineering, and domain-specific knowledge. Machine learning is one of the most important areas within modern artificial intelligence. Its central idea is that a system can improve its performance by learning from data. Instead of requiring a programmer to write every rule by hand, a machine learning system is trained on examples. From those examples, it identifies patterns and relationships that can be used to make predictions, classify new cases, detect unusual behavior, or support decisions. This distinction matters because early artificial intelligence relied heavily on symbolic reasoning. In those systems, experts attempted to encode knowledge directly into rules, logic statements, and predefined representations. A system might be told what conditions should lead to what conclusion. That approach can be useful when the problem is clear, stable, and rule-based. However, many real-world problems involve uncertainty, incomplete information, ambiguity, noise, and data. In those settings, it becomes difficult to write rules that cover every possible case. Machine learning emerged as a response to this limitation. Rather than telling the system every rule in advance, we provide data and allow the system to learn patterns from that data. In a classification problem, the system may learn which characteristics separate one category from another. In a prediction problem, the system may learn how different variables are related to an outcome. The key point is that the model can use data to detect regularities and apply those regularities to new situations. As we begin this module, it is also important to recognize the scope of artificial intelligence. AI includes machine learning, but it is not limited to machine learning. It also includes knowledge representation, planning, reasoning, intelligent search, perception, natural language processing, robotics, and decision-making systems. Some AI systems are data-driven. Others rely more on structured knowledge, rules, or optimization. Machine learning has become central to modern AI because today's problems often involve high-dimensional data. Each observation may contain many features, variables, signals, or measurements. Images contain pixels. Text contains words and semantic patterns. Network activity contains timing, volume, source, destination, and behavioral information. Business data may include transactions, customer behavior, operational records, and market conditions. In these environments, rule-based approaches are often too rigid, while machine learning models can detect patterns that would be difficult to specify manually. However, we should be careful not to treat machine learning as magic. A model does not become intelligent simply because it is trained on data. Its usefulness depends on data quality, algorithm choice, problem definition, and evaluation. A poorly framed problem can produce misleading outputs. A biased dataset can produce biased predictions. A model trained in one context may fail when applied elsewhere. This module serves two purposes. First, it introduces the basic language of the field: artificial intelligence, machine learning, deep learning, supervised learning, unsupervised learning, reinforcement learning, training, evaluation, generalization, and deployment. Second, it encourages a critical mindset. We are not only asking what these systems can do, we are also asking how they work, what assumptions they make, what data they depend on, and how their outputs influence decisions. By the end of this module, the goal is not merely to memorize definitions. The goal is to build a foundation that allows us to reason carefully about AI and machine learning systems. When we encounter a model, we should be able to ask what problem it addresses, what data it uses, how it learns, how it is evaluated, and what risks or limitations may appear. That foundation is essential because artificial intelligence and machine learning now shape decisions in many domains. Understanding these systems requires technical awareness, but it also requires judgment. Artificial intelligence is best understood as a broad field concerned with building systems that can perform tasks associated with human intelligence. When we say human intelligence in this context, we are not saying that a computer thinks or understands in the same way a person does. We are saying that the system is designed to carry out functions that usually require intelligent behavior. These functions include reasoning, learning from experience, perceiving patterns, making decisions, or selecting an action based on available information. This broad scope is important. Artificial intelligence is not one method, one tool, or one algorithm. It is an interdisciplinary field that draws from computer science, mathematics, statistics, logic, cognitive science, engineering, and applied domains. Some AI systems solve problems using formal reasoning. Others recognize images, process language, search possible solutions, plan actions, or support decision making under uncertainty. Historically, early AI relied heavily on symbolic approaches. In those systems, knowledge was represented through explicit rules, logic, and predefined structures. A system might be given statements about the world and rules for how to reason from those statements. This approach made sense for problems that could be expressed in logical terms. If the rules were known and complete, then the system could follow those rules to reach a conclusion. However, many real-world problems do not behave that neatly. Real data is often incomplete, noisy, ambiguous, or too large to describe with simple rules. Human behavior, medical images, financial transactions, customer patterns, cyber activity, and natural language all contain variation. In these contexts, it is difficult to program every possible condition in advance. Machine learning became important because it offers a different approach. Instead of relying only on explicitly programmed rules, machine learning enables systems to learn patterns directly from data. The programmer does not write every decision rule by hand. Instead, the system is given examples, measurements, or observations, and the learning process identifies relationships that can be used to make predictions or decisions. In traditional programming, we provide the rules and the input, and the program produces the output. In machine learning, we provide data containing inputs and known outputs, and the model learns a pattern that can later be applied to new cases. Machine learning is powerful when the problem involves large volumes of data or complex relationships. A model can analyze many variables at once and detect patterns that may not be obvious through manual inspection. This is why machine learning has become central to modern artificial intelligence, and it allows AI systems to operate where uncertainty, ambiguity, and scale make rule-based systems insufficient. At the same time, AI remains broader than machine learning. Modern AI still includes knowledge representation, planning, reasoning, and intelligent search. Knowledge representation focuses on how information about the world can be structured so a system can use it. Planning focuses on choosing actions to achieve a goal. Reasoning focuses on drawing conclusions from available information. Intelligent search focuses on exploring possible solutions efficiently. Machine learning connects strongly with these areas because learning from data can improve how systems perceive information, make predictions, or guide decisions. But we should not reduce all artificial intelligence to machine learning. A complete understanding of AI requires recognizing both the data-driven side and the reasoning-based side. The fundamental concept then is that artificial intelligence refers to the larger goal of creating systems capable of intelligent behavior, while machine learning refers to one major approach for achieving that goal through data. Machine learning gives systems the ability to learn patterns rather than depend only on fixed instructions. This distinction also helps us understand the practical scope of the field. AI can support automation, analysis, prediction, planning, and decision support. Machine learning can be used when data contains useful patterns that can be learned and applied. Together, they form the foundation of many modern technologies, but their effectiveness depends on clear problem definition, appropriate data, model development, and responsible evaluation. As we move forward, keep this foundation in mind. Artificial intelligence is the broad field. Machine learning is a central method within that field. AI seeks intelligent behavior. Machine learning seeks data-driven pattern learning. Understanding both ideas allows us to evaluate these technologies with technical clarity and practical judgment. Artificial intelligence, machine learning, and deep learning are closely related terms, but they should not be treated as interchangeable. Artificial intelligence is the broadest category. It includes any computational method designed to enable intelligent behavior. That behavior may involve reasoning, searching for solutions, applying rule, interpreting information, learning from data, or supporting decisions. Because AI is the broadest concept, it includes both traditional rule-based systems and modern data-driven approaches. A traditional AI system might rely on explicit rules. This system may contain predefined logic that tells it what conclusion to reach when certain conditions are present. In that kind of system, the intelligence comes from the structure of the rules and the way the system applies them. The system may not learn from data at all. It may simply follow the knowledge representation and reasoning process created by human designers. Machine learning is narrower than artificial intelligence. It is a subset of AI focused specifically on systems that learn from data. A machine learning model is not simply following a fixed list of manually written rules. Instead, it uses data to identify patterns, relationships, or regularities. Once those patterns are learned, the model can use them to make predictions, classify new examples, detect trends, or support decisions. This distinction is important because all machine learning is part of artificial intelligence, but not all artificial intelligence is machine learning. A rule-based expert system can be AI without being machine learning. A search algorithm used for planning can be AI without necessarily learning from data. Machine learning becomes relevant when the system builds its decision logic from examples. Deep learning is narrower still. Deep learning is a specialization within machine learning that uses multi-layered neural networks. The word deep refers to the presence of multiple layers through which data is transformed. These layers allow the model to move from simpler representations to more complex and abstract representations. In a deep learning model, the first layers may detect basic patterns in the input. Later layers may combine those basic patterns into more meaningful structures. This layered transformation is especially useful for complex data such as images, audio, text, and other high-dimensional information. The model can learn representations that would be difficult to design manually. However, deep learning should not be confused with all machine learning. Many machine learning methods are not deep learning. Linear regression, logistic regression, decision trees, random forests, support vector machines, clustering methods, and many other approaches belong to machine learning without necessarily using deep neural networks. Deep learning is powerful, but it is one branch with the larger machine learning family. The relationship can be understood as a nested structure. Artificial intelligence is the largest circle. Inside that circle is machine learning. Inside machine learning is deep learning. That means deep learning belongs to machine learning, and machine learning belongs to artificial intelligence. This nested structure also helps prevent a common misunderstanding. When people hear the term AI, they often assume the system must be using deep learning. That is not correct. An AI system may use symbolic rules, search, planning, reasoning, or other methods. When people hear machine learning, they may also assume it must involve deep neural networks. That is also not correct. Machine learning can involve many techniques that are simpler, more interpretable, or more appropriate for structured data. The practical difference among these terms affects how we evaluate technology. If a system is described as artificial intelligence, we should ask what kind of AI it uses. Does it rely on rule search, reasoning, data-driven learning, or some combination of these? If it uses machine learning, we should ask what type of model was trained, what data was used, and how performance was evaluated. If it uses deep learning, we should consider the structure of the neural network, the amount of data required, and the interpretability challenges that may come with layered representations. Therefore, the key idea is that artificial intelligence is the broad goal of enabling intelligent behavior. Machine learning is a data-driven subset of AI, and deep learning is a neural network-based subset of machine learning. Not all AI learns from data, and not all machine learning uses deep learning. Understanding this hierarchy gives us clearer language, better technical judgment, and a stronger foundation for evaluating AI systems in real-world contexts. Machine learning can be organized into major categories, and this classification helps us understand what kind of problem a model is designed to solve. The three categories emphasized here are supervised learning, unsupervised learning, and reinforcement learning. Each category uses data differently, each has a different learning goal, and each is appropriate for a different type of task. Supervised learning is the most familiar form of machine learning for many introductory applications. In supervised learning, the model is trained with labeled data. A label means that each input example is connected to a known output. The model sees examples where the answer is already provided, and it learns a relationship between the inputs and those outputs. The central goal of supervised learning is to learn a mapping from inputs to outputs. Once that mapping has been learned, the model can receive a new input and produce a prediction. If the output is a category, the task is classification. If the output is a numeric value, the task is regression. Classification asks which group or class an example belongs to. Regression asks us what value should be predicted. The important point is that supervised learning depends on examples with known answers. The model is learning from cases where the correct output has already been assigned. That makes supervised learning useful when historical data contains both the features and the outcome we want the model to predict. Unsupervised learning is different because the data does not include explicit labels. The model receives data, but is not told the correct category, answer, or outcome for each example. Instead, the goal is to identify patterns, structures, or relationships within the data itself. This kind of learning is useful when we want to explore data and discover organization that is not already labeled. Clustering is a common unsupervised learning technique. In clustering, the model groups similar observations together based on patterns in the data. The groups are not given in advance. They are discovered by the model. Dimensionality reduction is another common technique. It reduces the number of variables while preserving meaningful structure, which can make complex data easier to analyze, visualize, or use in later modeling. Unsupervised learning is not about predicting a known answer. It is about discovering structure. A supervised model is judged by how well it predicts known outputs. An unsupervised model is often judged by whether the discovered patterns are meaningful, useful, or interpretable. Reinforcement learning is different from both supervised and unsupervised learning. In reinforcement learning, an agent learns through interaction with an environment. The agent takes actions, receives feedback, and adjusts its behavior over time. That feedback usually comes in the form of rewards or penalties. The goal is not simply to predict a label or discover a cluster. The goal is to learn a policy. A policy is a strategy for choosing actions. The agent learns which actions tend to produce better outcomes and which actions should be avoided. Over time, the agent attempts to maximize cumulative reward, meaning it tries to make choices that lead to the best long-term result. This idea of cumulative reward is important because reinforcement learning often involves sequential decisions. An action taken now may affect what options are available later. Therefore, the agent must learn from consequence across time. It must balance immediate feedback with future outcomes. These three categories give us a framework for thinking about machine learning problems. If the data includes known outputs and the goal is prediction, the problem is supervised learning. If the data has no labels and the goal is to find hidden patterns or structure, the problem is usually unsupervised learning. If the system must learn by acting in an environment and receiving rewards or penalties, the problem is reinforcement learning. This classification matters because choosing the wrong learning type can lead to a poorly framed project. A classification problem should not be treated as clustering if known labels already exist, and prediction is the goal. A discovery problem should not be forced into supervised learning if there is no meaningful outcome variable. A sequential decision problem may require reinforcement learning rather than a static prediction model. As we continue studying machine learning, this classification will help us connect the problem, the data, the learning process, and the evaluation method. Supervised learning learns from labeled examples. Unsupervised learning finds structure in unlabeled data. Reinforcement learning learns through action, feedback, and reward. Together, these categories define the basic ways machine learning systems learn from experience. Data is the foundation of machine learning because every model depends on the information used to train it, test it, and interpret its performance. A machine learning model does not learn in isolation. It learns from data. That data may contain examples, measurements, labels, features, outcomes, observations, or records from a domain. The model uses that information to identify patterns and relationships. Therefore, model quality depends not only on the algorithm, but also on the quality, quantity, and structure of data. This point is essential. A sophisticated algorithm cannot fully compensate for poor data. If the data is incomplete, biased, inconsistent, outdated, or poorly organized, the model may learn patterns that are inaccurate or misleading. A model may appear technical and objective, but its predictions are shaped by the data it has seen. During training, the model adjusts its internal parameters in response to the data. These parameters determine how the model connects inputs to outputs. The training process changes those values so that the model better captures patterns in the example. In supervised learning, for example, the model compares predictions with known outputs and updates itself to reduce error. In other settings, the model may identify structure, reduce complexity, or optimize behavior based on feedback. Training is the process through which the model moves from raw information toward a learned representation of the problem. The purpose of training is not simply to memorize the examples. The real goal is generalization. Generalization means that the model can apply what it learned from observed examples to new unseen data. A model that only performs well on the data it was trained on is not useful in practice. It must perform well when it encounters future cases that were not part of training. Generalization depends heavily on whether the training data represents the underlying problem domain. If the training data reflects the conditions the model will encounter later, the model has a better chance of making reliable predictions. If the training data is narrow, distorted, unrepresentative, the model may fail when applied to real-world cases. This is why evaluation is just as important as training. Evaluation uses separate datasets to assess model performance. These datasets should not be the same examples used to train the model. If we evaluate a model only on data it already saw, we may confuse memorization with learning. The model may simply reproduce patterns from the training set without learning patterns that transfer to new cases. A separate evaluation process helps determine whether the model is learning general patterns or merely memorizing training data. Strong performance on training data, but weak performance on new data is a warning sign. It suggests that the model may be overfitting. Overfitting occurs when a model becomes too closely tied to details, noise, or accidental patterns in the training data. Evaluation also allows us to compare models, identify weaknesses, and decide whether a model is ready for use. Depending on the task, evaluation may focus on accuracy, error, precision, recall, false positives, false negatives, or other measures. The point is that evaluation gives evidence about whether the model works beyond the examples used to build it. Data also matters before training begins. Collection decisions influence what the model can learn. Processing decisions influence how the model receives information. Interpretation decisions influence how humans understand results. If data is collected from one population, one environment, or one period of time, the model may not generalize beyond that context. If data contains systematic bias, the model may reproduce that bias. For this reason, data is not a passive ingredient. It actively shapes model outcomes. The model reflects patterns in the data, including useful patterns and problematic ones. Incomplete data can hide important relationships. Biased data can produce unfair predictions. Noisy data can reduce reliability. Poorly structured data can make learning more difficult. To analyze the role of data, we must think about the full modeling workflow. We must ask where the data came from, what it represents, how it was prepared, what the model learned from it, and how performance was evaluated. Machine learning is not only about selecting an algorithm, it is about building a reliable connection between data, learning, evaluation, and real-world use. The central lesson is that data determines what a model can learn and how well that learning can be trusted. Training teaches the model patterns. Evaluation tests whether those patterns generalize. Data quality, quantity, structure, and representation influence both processes. Without careful attention to data, even the most advanced model can produce misleading predictions. Machine learning is applied across domains because it can extract insights from data and support decisions. This is one reason machine learning has become important in modern organizations. Many fields generate large amounts of data, but data alone does not automatically create knowledge. A dataset may contain patterns, signals, relationships, or warnings that are difficult for people to detect manually. Machine learning provides methods for finding those patterns and using them to support decisions. In healthcare, machine learning can analyze medical data, support diagnosis, predict patient outcomes, and identify patterns in medical images. The important idea is not that the model replaces clinical judgment. Rather, the model helps organize complex information and highlight patterns that support human decision making. A model may analyze patient measurements, records, or image features and produce information that helps professionals assess risk or identify areas that need closer attention. However, the human role remains essential because predictions must be interpreted in context. In finance, machine learning supports fraud detection, risk assessment, and investment strategies. Financial systems produce large volumes of transaction data, and some patterns may indicate suspicious activity. A model can examine transactions and identify behavior that differs from expected patterns. Machine learning can also help analyze the credit risk, market risk, or operational risk. Yet these applications require caution because financial data can change over time, and a past pattern may not remain reliable. In business and marketing, machine learning enables personalized recommendations, customer segmentation, and demand forecasting. Recommendation systems use behavior to suggest products, services, content, or actions. Customer segmentation groups people or organizations based on similarities in behavior, preferences, or characteristics. Demand forecasting uses data to estimate future needs. These applications show how machine learning can support strategic and operational decisions. A business may use recommendations to improve customer experience. It may use segmentation to understand different groups. It may use forecasting to plan staffing, inventory, supply chains, or marketing efforts. The value comes from using data to make decisions more informed and responsive. In cybersecurity, machine learning can detect anomalies and identify potential threats by analyzing network activity. Cybersecurity data often includes communication, timing, volume, access behavior, and system activity. A model can learn what typical behavior looks like and flag activity that appears unusual. This can help security teams notice possible attacks, misuse, or system compromise. However, anomaly detection is not perfect. Unusual behavior is not always malicious, and malicious behavior may sometimes look normal. Therefore, machine learning should be understood as a decision support tool, not an automatic guarantee of security. Its outputs need review, validation, and integration with broader security practices. Across all these domains, real-world applications raise important concerns about bias, interpretability, and ethical use. Bias can appear when training data reflects unequal patterns, incomplete representation, or historical unfairness. If a model learns from biased data, it may reproduce or amplify those patterns. Interpretability matters because people need to understand why a system makes certain predictions, especially when outcomes affect lives, finances, opportunities, or safety. Ethical use also requires attention to transparency, fairness, and reliability. Transparency means users and decision makers should understand the role of the system and the limits of its predictions. Fairness means systems should be evaluated for unequal impact across groups. Reliability means models should perform consistently enough to be trusted where they are deployed. Effective deployment requires more than technical performance. The organization must consider how the model fits into workflows, who reviews its outputs, how errors are handled, and how performance is monitored over time. Evaluating real-world applications requires both technical understanding and critical thinking. We need to ask what data this system uses, what outcome it predicts, how accurate it is, what errors it makes, who may be affected, and how the prediction influences decisions. The central point is that machine learning can be powerful across healthcare, finance, business, marketing, and cybersecurity because it helps transform data into actionable insight. But responsible use requires careful evaluation. A model should not be judged only by whether it can produce an output. It should be judged by whether that output is accurate, fair, interpretable, reliable, and appropriate for the decision.